Have you ever wondered how scientists separate mixtures in the lab? Today, we dive into the fascinating world of chromatography. This technique, which might seem like a modern marvel, has a rich history dating back to the early 20th century. It was first developed by a Russian botanist named Mikhail Tsvet, who was engrossed in the study of plant pigments. Tsvet was on a quest to understand why and how plant leaves change color. He discovered that when he poured a mixture of plant pigments through a column of calcium carbonate powder, the various pigments separated out into distinct bands of color as they moved down the column. This was due to the different pigments interacting differently with the calcium carbonate, a phenomenon he coined as chromatography, a term derived from the Greek words chroma, meaning color, and graphein, meaning to write. Over time, this technique has undergone numerous refinements and adaptations. What started as a simple column of calcium carbonate has evolved into a variety of chromatography types, each with their own specific applications. Today, chromatography is an essential tool in a plethora of scientific fields, ranging from chemistry and biology to forensics and environmental science. It's used for tasks as diverse as testing the purity of drinking water, identifying illicit substances in forensics, and even exploring the composition of distant stars in astrochemistry. Through these advances, chromatography has become more sensitive, more precise, and more versatile, expanding our ability to explore the world around us on a molecular level. From humble beginnings in a botanist's quest to understand the colors of nature, chromatography has grown into a powerful technique that is used in laboratories worldwide. With each new development, it continues to reveal the hidden complexities of the world around us, one molecule at a time. So the next time you see a beautiful autumn leaf or a vibrant flower bloom, remember the scientific legacy that brought us the ability to decode the colors of nature. Stay tuned as we delve deeper into various types of chromatography in the upcoming scenes. From its humble beginnings, chromatography has grown into a powerful technique used in laboratories worldwide. So, what exactly is chromatography, and how is it classified? Well, let's break it down. Chromatography is a powerful technique used in laboratories around the world. Its primary purpose: to separate mixtures. Imagine you've got a bowl of mixed fruit, and you want to separate the apples from the oranges, the bananas from the grapes. Chromatography, in essence, does just that, but on a much smaller scale, dealing with molecules and compounds. Now, on to its classifications. There are two main types of chromatography: planar and column. As the name suggests, planar chromatography involves a flat plane on which the separation occurs, while column chromatography uses a tube-shaped column. Let's focus more on planar chromatography for this episode. This type is further divided into two subtypes: thin layer chromatography, or TLC, and paper chromatography. In both these cases, the separation takes place on a flat surface. The difference lies in the stationary phase. For TLC, it's a glass, metal, or plastic plate coated with a thin layer of adsorbent material like silica gel. In paper chromatography, as the name suggests, the stationary phase is a special type of absorbent paper. These two techniques have their unique advantages and applications. For instance, TLC is often used in forensics to analyze the dye composition of fibers in crime scenes, while paper chromatography finds its use in the food industry to identify and separate food colorings. But wait, there's more. There's a high-performance version of TLC known as HPTLC, or high-performance thin layer chromatography. It's essentially TLC on steroids, offering higher resolution and quicker analysis time. With this understanding of what chromatography is and how it's classified, we're now ready to dive deeper into planar chromatography. First up in our exploration of planar chromatography is thin layer chromatography, or TLC. This remarkable technique, much like its sibling methods in the chromatography family, is all about separating the components of a mixture. But what sets TLC apart? In the world of chemistry, TLC is hailed for its simplicity, affordability, and speed. It's an easy way to identify substances, check the purity of a sample, or monitor the progress of a reaction. And it doesn't require a lab full of high-tech equipment. Picture this. A thin layer of adsorbent material, often silica gel or alumina, is spread evenly on a flat, inert substrate. This is the stationary phase. A sample of the mixture to be separated is then applied to this layer. Next, the plate is placed in a solvent. This solvent, or the mobile phase, ascends the stationary phase by capillary action. As it travels, it carries the components of the mixture along. But here's the catch. not all components travel at the same speed. Why is that? Well, it all boils down to the interactions between the stationary phase, the mobile phase, and the components of the mixture. Components that interact more strongly with the stationary phase move slower, while those that interact more with the mobile phase move faster. And voila! Our mixture is separated into its individual components, each appearing as a spot on the chromatography plate. The distance each component travels can be used to identify it. But TLC isn't just a one-trick pony. It's not only used in labs for chemical analysis, it's also used in forensics to identify drug substances, in environmental testing, to detect pollutants, and even in the food industry, to control quality. TLC, with its simplicity and effectiveness, has proven to be a vital tool in chemical analysis. So, the next time you hear about a mysterious mixture being separated or an unknown substance being identified, remember the humble thin layer chromatography. It might just be the unsung hero behind the scenes. Now, let's kick it up a notch with high-performance thin layer chromatography, or HPTLC. You may remember TLC from our previous discussion, but HPTLC takes things to a whole new level. It's like the superhero version of TLC, bringing higher resolution and precision to the table. So what makes HPTLC so special? Well, it's all about the details. HPTLC uses thinner layers of adsorbent material on the stationary phase. This allows for a better resolution, so you can separate components that are very similar in their chemical properties. It's like being able to tell apart identical twins based on their personalities rather than their appearances. But that's not all. HPTLC also boasts of a higher sample throughput, meaning you can analyze multiple samples simultaneously. Imagine being able to juggle several balls at once without dropping any. That's the kind of efficiency we're talking about. What's more, HPTLC uses smaller particles, which means faster migration of the solvent. It's like having a supercharged car in the world of chromatography. This not only speeds up the process but also enhances the separation of components. The advantages of HPTLC over TLC are quite impressive. The increased resolution and speed, combined with the ability to handle multiple samples, make HPTLC a preferred choice for many scientists. It's like choosing a smartphone over a landline. Sure, both can make calls, but the smartphone can do so much more. HPTLC finds its application in various fields such as pharmaceuticals, food and beverage industry, environmental monitoring, and even forensics. It's like a master key that can unlock multiple doors. In conclusion, HPTLC is a more advanced, efficient, and precise version of TLC. It's like comparing a bicycle to a race car. Both can get you to your destination, but the race car does it faster and with more style. HPTLC has taken the benefits of TLC and amplified them, providing scientists with an even more powerful tool for separation. So, next time you're faced with a complex mixture, remember, HPTLC might just be the superhero you need. Last but not least, we come to paper chromatography. A classic in the world of separation techniques, this form of planar chromatography is as straightforward as it sounds, employing paper as the stationary phase. To put it simply, paper chromatography is a method that uses a piece of paper as its stationary phase and a liquid as its mobile phase. When a drop of the mixture is placed onto the paper and the edge of the paper is dipped into the liquid, the components of the mixture travel up the paper at different rates. This happens because each component interacts differently with the paper and the liquid. Those that are more attracted to the paper will travel slower, while those more attracted to the liquid will travel faster. This method is not just about separating colors on a piece of paper. It has real-world applications in many industries. For instance, in forensic science, it's used to analyze inks and dyes, while in the food industry, it helps to identify and separate food colorings. The beauty of paper chromatography lies in its simplicity. It doesn't require complicated equipment or procedures, yet it provides an effective way to separate mixture components based on their different properties. It's a testament to the fact that sometimes, simplicity is indeed the ultimate sophistication. Despite its simplicity, paper chromatography is a useful and effective method of separation. So, there we have it, a journey through the world of planar chromatography. We've traveled from its captivating history to the intricate classifications, and explored the three fascinating types: thin layer, high-performance thin layer, and paper chromatography. Each with their unique characteristics and applications, they play a crucial role in separating mixtures in the scientific world. Remember, The world of science is always evolving, so keep exploring, keep learning, and stay curious. Subscribe for more because you won't find me later.